Hello everyone, and welcome to this PV Tech Talk Series webinar. My name is Mark Osborne, the Senior News Editor at PV Tech. Today, we have partnered with Trina Solar's Tracker Business Unit, TrinaTracker, for a deep dive analysis of its Agile dual-row tracker system. This will be looking at the latest developments in tracker design, components, and software solutions for the era of large format, high performance modules. This will also include a presentation from DNV on the many key requirements to ensure the bankability of the new generation of tracker systems. As always, we will have time for around a 15-minute Q&A session at the end, so please use the questions section during the presentation time. Our presenters today will be Jason Dion, Head of the Tracker Business Unit of Trina Solar, Cesar Hidalgo, Principal Engineer, Solar Energy Systems at DNV, and Antonio Marhello, the Head of Product and Engineering at TrinaTracker. So if our presenters are ready, Jason, I will hand over to you to start the presentations. Thank you.
Thanks for the introduction, Mark. So let me begin by giving a brief overview of TrinaTracker. Our tracker business started back in 2018 when we took a 50% shareholding in Enclave, a leading Europe tracker supplier, which was among the top 10 in 2017 in terms of global shipments. Initially, we promoted the tracker together with modules and inverters as a total service solution for our customer in the form of Trina Pro. In 2020, we went on to acquire the remaining share in Enclave and rebranded the tracker business as TrinaTracker. This decision was due to a change in corporate strategy to better cater for customers' needs in terms of both product and service. So now, in addition to the Trina Pro total solution, we can also offer trackers independently. After integration of Enclave, our tracker business has been upgraded and has become more globalized. We now have 4 production centers in Spain, Brazil, Argentina, and China. We can offer up to 7 gigawatts of annual capacity and 10 offices and branches all over the world. Up to now, TrinaTracker has installed over 5 gigawatts globally across 40 countries. Under the TrinaTracker brand, our product portfolio contains 2 types of tracker, Vanguard and Agile. The Vanguard series is based on independent rows with a 2-portrait design, with the new Agile series based on a dual row, one, and it's the Agile series we are launching today. Let me now hand over to Cesar and the DNV for his presentation on the methodology for tracker bankability.
Thank you very much, Jason. Thank you very much, the organizer, for this opportunity. My name is Cesar Hidalgo. I'm a principal engineer to DNV. I'm going to talk about bankability of trackers. How to mitigate the investment risk in tracker technology. The topics of my presentation are going to be a small introduction to my company, DNV, and then we are going to discuss about what is bankability, what are the aspects to review, are the existing building codes enough for the structural calculation of trackers? Another question is necessary to undertake the dynamic analysis for trackers? And finally, we are going to talk about backtracking algorithms and the energy yield that is typically associated to these new backtracking algorithms. And finally, we will talk about conclusions, okay? So about DNV, we are DNV Solar Energy System. We are involved in all the phases of the projects, from feasibility, engineering and development, construction and commissioning and operation. I particularly I belong to a department working in Iberia and Latin America, and just to show you some numbers, some figures, we have reviewed 2.5 gigawatt of projects under financing, also 0.6 gigawatt of projects for refinancing in the last years. So that means 160 projects and 70 projects respectively in financing and refinancing projects. So the market in Iberia and Latin America is very active. I would say is booming. Okay. Then we are going to talk about bankability. So that is a big question, because everybody's saying about my product is bankable, and we made the question to the bank, to a major bank, and then the response is from the bank is bankability means that the bank is convinced to the greatest possible extent that the cash flows are stable and the loan will be repaid. So the key points here are basically stable and secure cash flows. So in order to have these stable and secure cash flows, then we have to consider many aspects. In our methodology that is described in this slide, basically we consider from certification, we review the raw materials, we review the design adequacy for the site conditions that is going to be explained in a further slide. We talk with the manufacturer about the operation and maintenance approach that they have, and we also evaluate the lifetime expectation, especially today that there are some developers that are considering more than 25 years lifetime expectation. Another point of our review is basically to look at the manufacturing quality control, all the traceability, bill of materials, logistics, and after sales department. Finally, we look at the warranty terms. That's an important issue. You may have a good quality tracker, but if you have no standard warranty terms in the industry, then you are below the market practice. And finally, and not less important, is the track record of both the track record of the manufacturer and the track record of the product of the tracker. So all these things combined will give us an idea of the bankability of the tracker. I was discussing at the beginning about if the building codes that are available are suitable for PV trackers. And the short response to these questions is no. Unfortunately, they haven't been, provided for trackers calculations. So the compliance with those codes is not a total guarantee of lifetime. Eurocode or the American ASTI, they are not a total warranty for that. So you need to undertake further analysis. You need to undertake further studies, and particularly wind tunnels, static and dynamic wind tunnels are required. You can see here a picture of finite elements in one of the joints in the torque tubes of the trackers, in order to show you that the level of detail that is required in the calculations, in order to know if there is any point with non-adequate efforts, in the material. So that's important, because there is a risk in the trackers about the aeroelastic instabilities. The trackers are flexible structures, and then they can suffer the typical instabilities reported in that case, like buffeting, the vortex. You can see in the picture an image of the vortex around a cylinder, and the aeroelastic deflection, the torsional flattering, galloping, or the torsional divergence. All these elements are risky for the trackers. And why they are risky? Basically because you can see damages, catastrophic damages at much lower wind speeds than the design wind speeds. So we are talking at relatively low wind speeds, about 20 to 40 kilometers per hour, that you can have this amplification of the loads. And basically the structure is not dissipating the energy that is receiving from the wind. So this amplification can produce these catastrophic failures, and this is why the aeroelastic instability of the tracker has to be studied. And another point that I had in my presentation was to talk a little bit about the 3D backtracking algorithms. These new backtracking algorithms are allowing to cover complex terrain where PV trackers are being installed. So this complex terrain means that every tracker has to move individually, like in this picture on the left side, that is coming from our software Solar Farmer. And then the trackers are moving individually in order to optimize, the shading. So you will not see any more blocks of thousands of PV trackers moving at the same time, but on the contrary, you will see individual trackers moving in order to compensate the shadings. So this new backtracking algorithm means that you can see on the right picture in blue line the standard backtracking, and in red line is a new 3D backtracking, and you can see that at the beginning of the day, you can see how the 17.5% of losses of the standard backtracking is reduced up to 2.5% with the new backtracking systems. So we are talking in the experience of DNV that in a complete year, you can have up to 1% net energy gain for slopes between 4 and 6%. So obviously, if you have a terrain much more complex than 6% slope, you are expected to have a better net energy gain. Okay. So, and then we go to the conclusions. Basically, the PV tracker industry, in our opinion, is lacking of standardization. So there are some issues like the application of building codes that are not made for trackers that should be corrected in the future. So that is why we say that is lacking of standardization. There is another big conclusion, that is the bankability of trackers means the review of many parameters. So it's not just the price, it's not just the track record, for example, but it's also a lot of things that you have to look at before giving the label of bankable. There are many parameters behind this label. And then we have discussed a little bit about hot topics in the industry, like hot topics like the optimum design for aeroelastic instabilities or the new backtracking algorithms. So that's are two of the topics that we have discussed in my presentation. And I would like to finalize my presentation with a couple of remarks. DNV has been undertaking PV tracker bankability reports for the last years, and we published a guideline that is available in internet in 2019 with a lot of recommendations for people looking for bankability of PV trackers. And DNV has been particularly involved in the bankability reports for the Agile and Vanguard trackers from TrinaTracker. We have been participating. We are working actively with Trina trackers in these developments. And then thank you very much for your attention. Thank you very much. And then I pass over to Antonio.
Thank you very much, Cesar, and thank you very much, Jason, for your presentations. I am Antonio Moralejo Gil, Head of Product and Engineering at TrinaTracker, and I'm going to focus my part of the webinar in the presentation of our Agile 1P. The Agile 1P is our new tracker. This tracker is the evolution of our current dual row single axis tracker. It has 1P configuration. The Agile can accommodate up to 120 modules per tracker, and this Agile has a new drive system. Within this slide, we can see the key mechanical components of the tracker. There are 5 key mechanical components from the left to the side. The first one is the drive system. The drive system has 2 slew-in drive joined by a cardan with 1 motor. In order to attach the modules, we have the Trina clamp. The third key component is the torque tube. We keep a standard shape of the torque tube in order to improve the supply chain efficiency. The fourth one is the spherical bearing, and the last one are the piles. Here it's important to highlight that we have included the option of the W and H piles in order to optimize the driving works, especially for difficult ground conditions. Now, let's focus on the 2 patented key components that we have in our Agile trackers. In the left side of the slide, you can see the spherical bearing. And what is the spherical bearing? The spherical bearing is the piece or the component which connects the piles and the torque tube and allows the torque tube to rotate. This component is made in plastic with a very high resistance to solar degradation, and it's important to highlight that we installed our first tracker with this component 12 years ago. Therefore, this component has been tested in a hard environment during the last 12 years. The advantages of the spherical bearing comparing with the traditional cylindrical bearing are that this bearing allows us to avoid the need for calibration during installation process, minimize the additional stress on the torque tube, and enable us to increase the ramming tolerance. If we look at the right side of the slide, we can see our second patented component in the tracker is the Trina clamp. The Trina clamp is the component which connects the torque tube and the modules. This component replaces the traditional purling rail, module rail or purling, and with the special design of this component, we can save up to 50% module installation time. We have used this component in our previous 1P trackers, and we have updated the design to accommodate or to fit the new size of the modules. Now, let's focus on the Agile system features. I have separated the features in 3 groups. The first one is the design features, or are the design features. The second one are the hardware features. And the third group is the software features. Let's start with the design. We are going to talk about the tracker and module compatibility. As you are aware, this is the hot topic in the industry. If you look at the table below, you can see the evolution of the size of the modules from the typical 450 watts module to the new 670 watts module. For example, from the point of view of the width of the module, the dimension has changed from about 1 meter to 1.3 meters. And about the module length, the dimension has changed from 2 meters to about 2.4 meters. The module width impact dramatically in the length of the tracker, and the module length changed completely the core length. Therefore, it's quite important to consider the new size of the modules to design the trackers. We have considered this new size of the modules, and therefore we can say that our tracker is fully compatible with the new size of the modules. In this slide, we have included the modules from Trina, but it's important to highlight that our tracker is fully compatible with other type of modules as well. About the wind design, as Cesar commented in his presentation, trackers are flexible structures, even with frequencies higher than 1 Hz. What that means? During the structural verification, we need to consider at least the static behavior of the system, the dynamic behavior of the system, and for sure the aeroelastic behavior of the system. In order to consider these three behaviors, we have carried out a new wind tunnel test with collaborating with CPP. We have done we have carried out a wind tunnel pressure model test in order to define the pressure coefficients, and 3D full aeroelastic tests in order to check the aeroelastic behavior of the system and to define the critical wind speed. And we have carried out an on-site plug test in order to measure the dynamic parameters of the system. Frequency is more or less easy to define or to calculate using finite element analysis. However, damping is much more difficult. Therefore, it's always recommended to carry out this kind of on-site plug test in order to measure directly the dynamic parameters of the system. In order to mitigate the wind effects on the tracker, we follow two different strategies that I'm going to explain. In the left side, you can see the wind stow strategy. This strategy is defined following the results of the 3D full aeroelastic test. In this case, in the case of the Agile, the stow angle of the system is at height tilt angles. And if you look at the right side of the slide, you can see the tailored tracker layout. This is the second wind mitigation strategy. We reinforce the border tracker of the plant in order to consider first the location of the trackers in the plant, and second, the wind direction. If you look at the pictures, the blue one are the reinforced tracker or outer tracker, the gray one are the border tracker or reinforced tracker, and the green one are the inner tracker or standard tracker. Using different type of trackers, depending on the location of the plant and wind direction, allows us to optimize the design of the plant. But the wind is not only the weather conditions that we need to consider. In order to consider other operational weather conditions, we have defined an integrated alarm strategy. This integrated alarm strategy has 6 types of alarms. In the left side of the table, you can see the 3 alarms related to operational conditions, and in the right side of the table, you can see the 3 alarms related to weather conditions. The alarms related to operational conditions are the low battery alarms, communication alarms, and manual store alarms. And the alarms related to weather conditions and the hail storm, the wind alarm, and the snow alarm. Once we finish the explanation of the features from the point of view of the design, we are going to start with the hardware. First is the multi-drive. We have changed the drive system of the tracker from the traditional 1 linear actuator to a Sliwing drive. Why have we changed the drive system? First, in order to achieve a tracking angle of 60%. Second, in order to give more ease with a ground slope tolerance. Third, in order to achieve more is north-south ground slope tolerance. And finally, in order to allow to misalign the tracker between 2 rows. The misalignment that we can get is 12 degrees. With this misalignment, we can use more space to install our tracker. Now, in this slide, we have done a comparison between our Agile tracker and the traditional single row 1P tracker from the point of view of the length. Using our Agile tracker, we have 30% less tracker per megawatt, 45% shorter tracker, therefore less grading. We can save more or less 9% of DC cable, and combining these three conditions, we can optimize the BOS cost of the plant. If you look at the right side of the slide, we have done a small exercise in order to compare the number of trackers that we can accommodate in a typical layout plan. With our Agile tracker, we can accommodate up to 3 megawatts, comparing with the 2.6 megawatts that we can accommodate using the traditional single row 1P tracker. That means that a shorter tracker can use better the length than a longer tracker. Okay, we have discussed about the design, we have discussed about the hardware, and now we are going to discuss about the software. We have included a new SuperTrack algorithm in our trackers. The SuperTrack has 2 parts. If you look at the top of the slide, you can see the STI. The STI is the Smart Tracking Algorithm. This algorithm has designed especially for bifacial modules and modify the tracking angle considering the diffuse and reflected irradiance. According to our studies in China, we can get an energy gain up to 5%, especially in cloudy and overcast days. The second part of the algorithm is the SBA. The SBA is the smart backtracking algorithm, and this algorithm takes into account the height of the tracker due to the slope of the terrain. In order to avoid the shadows between trackers, this smart algorithm modifies the tracking angle of each tracker. As well, according to our measurement and in our studies in our Chinese test sites, for very complex terrain, we can achieve up to 3% of energy gain, especially during the early morning and late afternoon. And the second part of the software is the SCADA system. We have developed a new SCADA system. This SCADA system has two parts as well: the monitoring part and the control part. We have developed this system in order to give some advantages to the client to easy the operation and maintenance task. And this SCADA system has been developed based on our current TrinaTracker cloud. Our current TrinaTracker cloud is a monitoring system, and including the control in this monitoring system, we have developed the new SCADA system. Well, summarizing, the most here in this slide we can see the technical advantages of the system. The first one is the high reliability due to the use of multi-drive system, the use of shorter tracker design, and the use of advanced wind design based on the full 3D full aeroelastic test and pressure model test from CPP. The second is the optimized BOS due to the use of lower trackers per megawatt. The use of spherical bearing that allows us to increase the installation tolerance, and the use of Trina clamp that allow us to reduce the module installation time up to 50%. We have a greater power generation using our SuperTrack algorithm that has, as commented before, two parts: the smart tracking algorithm and the smart backtracking algorithm. And with the change of the sling drive and the use of shorter tracker design, we have enhanced the adaptability of the tracker to the complex terrain. And this is all from my side. Thank you very much for your time, and I'm going to hand over the presentation to Jason. Thank you very much.
Thanks, Antonio. So to conclude today's session, I'd like to end with a brief outlook on the development of the tracker industry. The industry currently focuses more on the wind tunnel test for structural stability, but software such as smart algorithms and monitoring platforms are also important for long-term planning. Tracker product development needs to consider the whole industry chain, including modules, inverters, clean robots, and so on. But at the moment, the tracker industry lacks unified mutual standards, which leads to an increase in transaction costs. Going forward, standards will need to be established and enhanced. With ongoing technology development, the introduction of well-established standards, and the integration of the whole industry chain, I believe the value of trackers will be greatly increased, which will see significant growth in their global marketing share. DNV has continued provided the valuable validation to TrinaTracker. So that's all from my side. Thank you, everybody. And now I will pass back to Mark for the Q&A. Thank you.
Well, thank you, Jason, and thanks everybody for coming on today. There's been a lot of great questions coming through. In fact, they're still flooding in, so you may have to bear with me a little bit while I try and sort these out. So, Antonio, a couple of questions here that are very, I think there's quite a few people basically have asked this type of question. Do the TrinaTracker trackers actually work with other modules than just those of Trina Solar? And basically confirm the compatibility. What's the range? Is it limited to only Trina Solar, or does it cover pretty much all types of large area modules today?
For sure, our tracker works with Trina modules and with other modules as well. When we have designed our new trackers, we have considered the new modules from Trina, obviously, and the new modules from other competitors. Therefore, we can say that our tracker is fully compatible with other module manufacturers as well. In fact, we are doing projects with other module manufacturers.
Okay, great. Another question here that I think covers other people's questions on this. It's a good question, actually. What are the most important considerations in choosing between the Vanguard product and the Agile product?
Okay, the main difference, as everybody knows, is the configuration. Is the Agile product is 1P configuration and Vanguard product is 2P configuration. Therefore, the number of foundation in 2P configuration is much lower than in 1P configuration, and we recommend to use the 1P configuration for flat terrains with no too complicated ground conditions and with shapes more or less regular shapes. And Vanguard is recommended for areas where the ground is quite difficult, and therefore makes sense to reduce the number of foundation and the soil risk as much as possible. This is the main conditions to choose one solution or another solution.
Okay. A lot of people keep on this topic, because a lot of people ask various different questions, some of them very technical, so we're not going to get time to go specifically into that, because I think you'd find that difficult. But I guess it's like which of the two different tracker systems between the Vanguard and the Agile are best for bifacial? Talk just generally. I know we only had time to cover a little bit about bifacial, but a lot of people actually asked a number of questions related to bifacial modules.
Generally speaking, there is not too many difference between Vanguard and Agile regarding the bifacial performance. Therefore, we want to say that the conditions that we have to consider in order to choose one solution or another solution are the ground conditions. If we want to minimize the number of foundations, therefore we need to choose 2P. And if our ground is quite soft or not soft, quite easy, or it's a normal terrain, 1P solution is the best one. Therefore, we don't want to focus the behavior of the tracker, because the bifaciality between 1P and 2P is quite similar.
Right. Yeah. Just back to, I think this question came in before you actually discussed with the Agile, the actual slope maximum angles. But someone was actually asking, so I thought would repeat this one. You know, what is the maximum slope recommended to ensure obviously good performance with the Agile system? And I think as well, you may want to reiterate that, you know, that I understood from your presentation that the performance actually improves, you know, relative to other trackers because it's designed to be adjustable. Maybe to give people a little bit more understanding of that.
Okay, our previous by-road tracker was the drive system of our previous Agile tracker was linear actuator. In order to improve the adaptability to the terrain and the tolerance, and following our experience in previous projects, we changed the drive system to the multi-drive system to a Sliwen drive system. The tolerance that we can achieve now are 10% east-west and 20% north-south. 10% east-west is not a limitation regarding the adaptability, the physical adaptability of the tracker. Is regarding the wind conditions. When the slope of the terrain increase, the wind speed increase. Therefore, we recommend to install the trackers in areas with lower east-west slopes than 10%.
Okay. I think maybe both of you, both Cesar and yourself, Antonio, could answer this in more general terms, but a couple of questions about, obviously this is a hot topic, is obviously on the wind dynamics. And it says, you know, what is the average speed, wind speed that is suitable? And it's interesting because it's over the lifetime of the trackers stroke panels. And also what is the maximum wind speed tolerable? I think that's very difficult to answer, you know, specifically, but I think both of you understand how important those questions have become in the last couple of years, especially now with large format modules.
Okay, I'm going to start with the answer of this question. Okay, there is no fixed maximum wind speed that the tracker can support, because we designed the tracker for each site conditions and wind conditions. Following the result of our wind tunnel test, we have chosen a new wind stow position at high tilt angles in order to avoid the instabilities of the system. Therefore, mainly the tracker design is governed by the static efforts. It's not possible to say my tracker allows 200 kilometers per hour, because depends on each project. We design our tracker adapted to each project.
Yeah, Mark, in DNB opinion, we are pretty much aligned with Antonio. So what we have seen is every project site has particular wind conditions seismic conditions, ground conditions, and everything has to be included in the structural calculation. So focusing only on the wind speed, that is one of the elements of the structural calculation, and we cannot give an answer like 100 kilometers or 120, or that depends on the site, and also on the the manufacturers like TrinaTracker and other manufacturers. They have a broad range of metal thickness, more metal, more rigidity, more stiffness, so that can be also adapted for every project. So I know that many people are talking about the wind speed like if it was a magic number, that
Yes, yes.
is 60 kilometers per hour or 70 kilometers per hour is better. Yeah, but it's quite specific of your site, so it's not a magic number.
Okay, because you mentioned there, I don't think we had a specific question on this, but if I notice with this topic in particular, it's not just high wind speed, it's a constant speed, but that it's often a slower speed than, say, what people would assume would be a catastrophic failure. Can you discuss that? Explain to people it's not just all about high speed, high wind speeds.
Yeah, and in one of my slides, I was talking about aeroelastic instabilities, this amplification of loads, and unfortunately, this is happening even at relatively low wind speeds. We are talking about 25 kilometers per hour. We have seen this phenomenon. So even if your tracker can go to a stow position after 25 kilometers, is the sign for after 25 kilometers, you can have these aeroelastic instabilities at 25. So that is so important that you analyze the aeroelastic instabilities in wind tunnels, like TrinaTracker has been doing, So it's quite recommendable to have this analysis done in order to see if your tracker is going to suffer this amplification of the loads that can be dramatic in your project, can have a catastrophic effect on your project. Yeah.
Okay, because another aspect there for both of you, I know obviously with the algorithms being able and connected with the weather stations, you're getting you're given now using intelligent resources, shall we say, to enable correct stowing with higher wind. But what is the situation when, say, and I've seen this actually on videos, that during the actual installation of modules onto a tracker system, you get some high wind come in. Is that preventable? I mean, is that something you just have to deal with? Because there's been videos out there showing people, showing that this isn't just a problem with an operating power plant, but actually you can get a gust of wind or a strong wind come in while you're actually assembling. So is there mitigation for that?
The key first is to measure the wind speed during the assembly. This is something that we always recommend, to install a self-power weather station in order to measure the wind speed during the installation, because it's not normal to measure the wind speed during the installation. And second one is to install the tracker, or to install the modules more than the tracker, because the problem comes when you are installing the modules, not when you are installing the tracker, the steel pieces. Is to install in the most stable position as possible, that in this case is at high tilt angles.
Right. Change a topic here, and I think actually both of you, this is relevant. Can the number of modules per tracker be specified by the customer, or is there certain modules that can accommodate a certain number? Sorry, actually, the tracker models that can accommodate a certain number of modules. Bit of a complicated one, but perhaps you can answer that one.
I think that I understand you. Yes, for sure the client can define the number of modules per string, only considering that the maximum length that we can achieve per row is 62 meters. Okay.
Yeah. And
62, sorry, no, 72. 72, sorry, 72. 72
okay.
meters. Yes.
Okay.
72.
Completely different question here, but I do like it because I've actually thought of this myself quite a lot. Is when you're looking at the connection between the rows, you've obviously got the connection bar. What do you do from the point of view? In fact, our screen shows it, but in sandy conditions. But what about if you've got grass? How does that affect the O&M activities of cutting grass with such a design?
Okay, the connection that connects both sleeve and drive is a cardan bar. Okay.
Yeah.
There is only one bar between two rows, to each rows. Okay. Therefore, there is a free corridor between two trackers, and in addition, the advantages of this bar is that it's located more or less 1.5 meters above the ground, and it's possible to disassemble. Okay, the solution is not thought to disassemble every day, but it's possible to disassemble the bar if it's necessary to pass through through that corridor. Okay.
Yeah. Another aspect here, I think this is just a general question, but I think a lot of people still, and I think this is a difficult question to answer, but maybe just give people some guidance on this for both of you. The difference between the decision making as to whether a tracker system is best for a project compared to a fixed tilted system. I mean, what would be the key criteria that you would, I mean, obviously you might say, well, always use trackers because you're selling them, but actually what are the considerations that you would say people need to look at to decide on that kind of decision making?
Okay, Mark, we have fixed tilt also. We install fixed tilt and we manufacture fixed tilt as well. Okay, we are tracker manufacturers and fixed tilt manufacturers. Normally, one of the key factors at least from the side of the manufacturers are the ground slopes. If the ground slopes are crazy, we do not recommend to use tracker. But this is a condition from the side of the manufacturers. There are other conditions from the side of the site of the plan or production or other different points that we don't usually evaluate. But from the point of view of the manufacturers, the slopes are one of the key challenge for us, because, for example, there are projects in Portugal or in Spain where the slopes are crazy, and we do not recommend to use trackers in that slopes. Never.
Yeah. Okay. There's been a couple of questions since we started the Q&A session. In fact, there's been a lot of questions since and I'm trying to get through some of these literally live. Issue about wiring, the actual cabling, how that is managed. We didn't really cover that in any detail at all, but what's the recommendations, or how does the TrinaTracker systems work from a wiring scheme point of view?
We have three options for wiring. Okay. Here I don't have the pictures to show, but if the person who is asking about this can share their details, I can share with them the details of the wiring for our trackers.
Got it. Okay, understood. We've had quite a few different questions about pitch, angles, stow points. Perhaps we could just let me just generalize and say, can you just give us a bit more information on obviously what the stow angles are suggested, and where do they differ, say for instance, between high wind event and maybe a weather event such as hailstorm? A lot of people are asking very specific things on the stow side, which I don't believe you really would be able to cover here, but just in general terms, is stowing exactly the same for both of those kind of events, or is there differences, and how does that work with the algorithms and how it interacts with the weather station? I guess you just try and bring a bigger picture together to give people, because again, we didn't cover a lot of that today.
As I commented in my presentation, we have integrate alarms in the tracker formed by 6 alarms, and the priority versus hail and wind is the wind, and the position about the hail and wind is slightly different, because the hail has more tilt angles than wind.
Got it. Yeah, understood. Looking at the time, we probably can squeeze in just one more question. And to be honest, apologies to everybody. There's been a significant amount of questions coming through today. From a company perspective, TrinaTracker is obviously the new business unit. Just reiterate the company's sort of capacity availability for trackers, because a lot of people may claim a capacity figure or production figure, but that would be total, and everybody is trying to operate in different countries. And you mentioned that you used a standard design in the tracker, but perhaps explain a bit more about the standard size that you're talking about. What does that really mean? Okay,
there are some countries, okay, that in order to do projects there, okay, the governments requires to use local suppliers, local content, and different things. Therefore, in order to simplify the supply chain, especially in countries where we don't have regular suppliers, we have specific suppliers for specific projects, we have decided to keep the square tube standard shape as the shape of our torque tube. We have evaluated to use other different solutions, but finally, in order to simplify and to meet the requirement in some countries like KCA or South Africa I can put a lot of examples. Requirements of local content, we decide to keep the standard shape of the torque tube as shape of the torque tube. The square shape of the torque tube, the shape of the torque tube.
Right. Okay. Well, we're really at the end here, and thank you, Cesar. Thank you, Antonio and Jason, for your presentations. I hope. Well, I can tell from the number of questions coming in, there's a lot for you guys to follow up with. And trust me, people, if your question wasn't answered, people will get in touch with you to help you, because there's only a certain amount that we can actually get through today. But I think we've actually done well to get through so many questions in the time. So once again, thank you for all those that have attended today. It's been a really, really enjoyable topic. I've thoroughly enjoyed working with the presenters to come together to give you this webinar today. And I just want to say thank you to everyone. And that's the end of the webinar. Thank you very much.
Thank you.
Thank you. Goodbye.